Welcome to my new calculus channel. I am John Gabriel. In the last lesson, that was lesson 6, we talked about the derivative and how to find the slope of a tangent line. And we saw several ways that we were able to demonstrate that if a secant line is parallel to the given tangent line, then they obviously have the same gradient or the same slope. In this video, which is a combination of lesson 7 and 8, we're going to examine the natural average and also area defined as the product of natural averages. They're called natural averages because that's very much the way that area or the concept of area was developed. So, for example, the Greeks defined plane numbers, which really are based on the concept of area. A plane number basically is really nothing more than an area. The sides are natural averages that correspond respectively to the average length or the arithmetic mean of the vertical line lengths and the average length of all the horizontal line lengths in a given rectangle. And we'll see very shortly how all that works. So, let's look at the very first applet here, which discusses area in terms of natural averages. So here we have a rectangle, which we can change the dimensions by moving this point upwards or moving this point across. And we can, for example, look at the horizontal lines. So if we take the average of those three lines, it'll be 2.9, won't it? Or even just the average of these two lines. And if we include more lines, notice that the average does not change. It's still 2.9. It's always 2.9, regardless of how many lines we have. So this side here, 2.9, is the average of all the infinitely many horizontal line lengths in this rectangle. Similarly, the vertical lines have as average the length of this line here. So if we take the length of these two vertical lines and average it, we will have 8.26, and it doesn't matter how many lines we have. It'll always be 8.26. So area really is just the average of these vertical lines, which is 8.26, times the average of the horizontal lines. Does that make sense? It's a pretty simple concept. And this is exactly what happens in every calculation of area or volume even. For example, what is volume? Volume is the product of three averages. And hypervolume would be the product of however many dimensions are being used. So area is the product of two averages and volume is the product of three averages. So this here describes to us how we came to the understanding of area. And I will show you later on, and you will see that this is exactly what we do when we integrate a curve and we find the area between the curve and the x-axis. Indeed, what we're doing is we're finding the average value between the curve, which is the average of the infinitely many ordinates in that interval, and we're multiplying it by the interval width, which is the average of the infinitely many horizontal lines. So let's close that applet and look at the next one, which just gives us a little example here of what I mean with the average of all the infinites with a straight line, and then I'll continue on to a nonlinear curve. So over here, if we want to know the average between these two vertical lines, what do? We just add 2.5, which is this length and this length here, and divide it by 2, right? So does it ever change? No. As you can see, it's always going to be 4, right? Always going to be 4. And we can also move this across here, and that is the only time the average will change, because the length of this line here and this line here change if I move the green points. Okay? So really what we have here is just the average of the infinitely many line lengths that are found in this interval, the vertical line lengths, not the horizontal lengths. That's the average, and then we multiply by the interval width, which is this distance down here. Yes? That distance will be the average of the horizontal line length. So from 1 to 3 we have 2, which is the average of all the horizontal line lengths. And from this ordinate to this ordinate, the average of all these line lengths is this middle one here, which is 2.4. So what we do is we simply multiply 2.4 by 2, and then we have the area that is formed under the curve. Okay, so well, in this case here it's 1 plus whatever that is, 3 I think. Whoops, let's put it exactly on 3. Not exactly. Okay, so 1 plus 3 is 4, divided by 2 is 2 times 2 is 4. So let's see again. 1 plus 3 is 4, divided by 2 is 2, so the average vertical line length is 2, and the horizontal average is also 2, because 3 minus 1 is 2, and 2 times 2 gives us 4. Okay? So we've seen how that works in terms of a straight line. Finally, I'd like to look at the last applet, which shows us how this works with a nonlinear curve. So you'll see over here that this blue line is the average line length of all the vertical line lengths in this trapezium, and likewise on the side here, this blue line is the average line length. The interval is the average of the horizontal line lengths, and if we multiply the two together, we have the area. On this particular curve here, the average value of all the vertical line lengths, which are the ordinates, is 3 1/3. And if we multiply it by the interval width, which is 16 minus 12, then we have the area, which is 13 1/3. So a natural average is the sum of all the vertical line lengths divided by the number of vertical line lengths. That just gives us the average that you see here, which is the length of the blue lines. Note that the pink or purple line lengths are also natural averages of the horizontal line lengths depicted in the yellow shaded areas. So what we're doing actually when we're calculating area is we're taking this irregular gray area and changing it into a rectangle. Do you see that? So blue now is the average length of all the vertical lines, and this pink line is the average of all the horizontal line lengths. Similarly in this case here, and we can just move that along and see what happens as we perform quadrature. By the way, that's where the term quadrature comes from. We're taking this whole gray area and just squashing this little gray part down into the yellow area here and forming a rectangle, which gives us the area. And I'm going to show you, you're probably wondering right now, how do we calculate the average of infinitely many ordinates? Well, there's a beautiful theorem called the mean value theorem, which allows us to do that, and we're not only going to find out how it works, but we're also going to prove it in the next lesson. So I recommend that you download these applets and also study these lessons. And for those of you who want to go further, Lesson 5, 6, 7 are all a little more advanced than what you've been used to so far in the previous 6 lessons, and I would actually study those articles that you see over there. I would hold off on differentiability and differentiation rules until we finish the next lesson, in which case you can just go ahead and study all these 10 lessons here in detail. And these are all available in PDFs at the site here that you see at the top. Okay, so that's pretty much it, and I'm glad you could join me. This is the New Calculus channel. I'm John Gabriel. See you next time.